So when you're working with alcohols, there are lots of ways to convert the alcohol into a leaving group. We can protonate it. Of course, that requires acid. We can use other reagents like SOCl2 or PBr3, and these will convert the alcohol to the OH to a Cl or Br. These are both really acidic reagents. They might not look it, but they're incredibly acidic. And then there's another. There's something called tosyl chloride, which everybody writes as TSCl. Tosyl chloride. So what is tosyl chloride? Tosyl chloride looks like this. It's a little bit bigger structure, and you might say, oh my goodness, this is what a mess. Well, this is why no one writes out the full structure of tosyl chloride. Everybody just writes TS. TS comprises that part of the molecule. Now, don't be ignorant about what tosyl chloride is, but everybody uses this shorthand. No one writes out this structure all the time. So, what's going to happen here? We're going to take an alcohol. I'm going to write a primary alcohol, and we're going to react it with tosyl chloride. And not just tosyl chloride, but a typical solvent, and I say it's typical, but it's what most people use, many people use, is pyridine. Now, what is pyridine? P-Y-R. Pyridine is a weak base. So this is in contrast to, we're going to make this alcohol into a leaving group. And we're going to do it not by treating it just with a strong acid and protonating it, or using these acidic reagents. In fact, we're going to react it under weakly basic conditions. Because sometimes that R group may contain functional groups that will fall apart. Things like esters. You just can't hit everything with these really strong acids and expect the molecule to stay in one piece. Sometimes you need more mild conditions, and tosyl chloride gives you this more mild way to convert your alcohol to a leaving group. So what happens is our alcohol is going to react with tosyl chloride. I'm not going to show the whole thing, but basically the alcohol attacks sulfur and kicks out this chlorine. This is almost like an SN2 reaction in its own right. Now, I'm not going to clean this up, but we'll then have this OH group to remove, and of course we have a base present. Anyway, the point is we'll get this structure. Most people wouldn't write it out this way. They just write OTS together. But the fact is, this oxygen is still intact. That oxygen attacked the sulfur. It is still part of the molecule. Occasionally, and this is wrong, people will write, oh, I want to make a tosylate, a tosyl group. That is not a tosyl group, okay? The oxygen is still present. Now, as it turns out, this is a great leaving group. And when you see this, you can think, oh, this is just like having a bromide or an iodide here. Well, once you form a tosylate, and if it behaves just like a bromide or iodide, then we can do any of the reactions we've talked about. We can do SN2 reactions. We could treat this with azide. Sodium azide, that would do an SN2 displacement. In fact, that'd be a really good one because I've shown this as a primary tosylate. You don't have to have a primary alcohol. You could do a tertiary alcohol and form a tosylate. So you can convert almost any alcohol into the corresponding tosylate, whether it's primary, secondary, tertiary. And then you can do all your reactions, SN2 reactions. You could do SN1 reactions, E2s, E1s. So this is a really flexible way to convert an alcohol into a leaving group without relying on acid. Now, we don't have to always worry about using acid. Lots of times it's just fine. But sometimes you need to be careful. When you have to be careful, people oftentimes use tosylate instead of some of these more acidic reagents.